types: molecular dispersions, colloidal dispersions, which will be our focus for the unit, and coarse dispersion. Coarse dispersions, you'll cover them in year 5, when you'll be looking at pharmaceutical emulsions and pharmaceutical suspensions, the formulation aspects. So molecular dispersions. Molecular dispersions are made of particle sizes of less than 1 nanometer, not 1 micron, 1 nanometer, are very small. They're actually not visible by the naked eye, and form true solutions of one component in another. They are visibly homogeneous, that is, they form very clear solutions. They do not scatter light because of their small size. Their particles are invisible under the electron microscope. Even with the electron magnification, you cannot be able to view molecular dispersions. Their particles also easily pass through semi-permeable membrane and filter paper. They undergo rapid diffusion, or what we also call Brownian motion. An example of molecular dispersions are ions and glucose. So these ones, you cannot see them even under the electron microscope. They are very small in nature. Now, colloidal dispersions, what will form our focus discussion. So their particle size, they range from between 1 nanometer to 0.5 micrometers. That's their size range. They scatter light, and therefore they appear turbid. They appear turbid in nature. Their particles are not visible under the ordinary light microscope, but you can visualize them under the electron microscope. The particles also can easily pass through a semi-permeable membrane, but do not pass through a filter paper. So they are blocked by a filter paper. The particle diffuse slowly as compared to molecular diffusions, molecular dispersions. Now, examples of colloidal dispersions under the natural systems, we have suspensions of microorganisms. Blood has colloidal components. We also have isolated cells in culture. Some synthetic polymers may form colloidal dispersion. And a good natural colloidal dispersion is the milk that we take, form of a colloidal dispersion. So for colloidal dispersion, you have to remember the size range is between 1 nanometer to 0.5 micrometer. 0.5 micrometers. Anything that falls within this range will form a colloidal dispersion. Now, last but not least, coarse dispersions. These have a particle size of greater than 0.5 micrometers. They also scatter light due to their size range, and therefore they'll appear cloudy or milky in nature. Their particles are also visible under the ordinary light microscope. That, of course, tells you that they can also be visualized by the electron microscope. Now, for coarse dispersion, the particles are not able to go through a semi-permeable membrane, and they are also not able to go through a filter paper. These particles also do not undergo diffusion. And examples is most pharmaceutical emulsions and suspensions that you'll cover in year 5 when you'll be looking at formulations. So that's just a brief introduction of disperse system. So we have molecular, colloidal, and coarse dispersion. So now, and the definition does not change. So what is a colloid or a colloidal dispersion? Is a system comprised of a disperse phase and a dispersion medium. And a good example is when a solid is dispersed in water. Now, what makes it a colloidal dispersion is the size range. The particles of the dispersed phase will fall between 1 nanometer and 0.5 micrometer. So we have an example, a sol, which forms a dispersion of a solid in a solid, or a dispersion of a solid in a liquid, or a dispersion of a solid in a gas. But most commonly, we used to describe it or a dispersion of a solid in a liquid. Now, the prefix denotes the dispersion medium. For example, when you have the term aerosol, I believe you've come across this term. Aerosol refers to a solid dispersed in a gaseous medium. So the medium is air. Hydrosol will be a solid dispersed in water. So the prefix hydro refers to the dispersion medium, which is water. So how do we classify colloidal dispersions? We classify them based on two aspects of classification. We have based on the physical states, the physical state of the dispersed phase and the dispersion medium. So we can look at these examples. So if you have the dispersed phase as a solid and the dispersion medium as a solid, so this is a solid dispersed in a solid, will form a solid sol. And a good example is zinc oxide paste. Zinc oxide dispersed in petrolatum. Where the dispersed phase is a liquid and the dispersion medium is a solid, the colloidal type formed is what we call a solid emulsion. The good example is absorption bases, where you have aqueous medium in hydrophilic petrolatum. Another example is cheese and butter that you come across in your homes. You can also look at other examples. You don't have to strictly stick to what I've provided. Where we have a gas as a dispersed phase, now a gas dispersed in a solid, we have what we call the solid form. An example is formed plastics. You've come across formed plastics. And pumice stone. These are stones that most of you maybe have used. Use it during bathing. You're bathing and you want to use it to sugua miguu. So this is what we call the pumice stone, and also formed plastics, so it's dispersed in a solid. Gas as a continuation from the physical state nature of classification, where you have a solid now dispersed in a liquid medium. This is what we call the sol. You can also refer to a gel. And a good example is magnesia and aluminum oral suspension. You also have tetracycline oral suspension. Some jellies and paints will also fall under this category. A liquid dispersed in a liquid, this forms an emulsion. And a good example is milk. Soybean oil in water, emulsion. And you also have mayonnaise. I think you've come across milk and mayonnaise in your day-to-day life. We also have a gas as the dispersed phase. The dispersion medium being a liquid, you have what we call a form. That will be a color type. And Examples is carbonated beverages, effervescent salts in water, shaving cream, and also whipped cream. Just to end up on the classification, a solid dispersed in a gas. So you have solid particles dispersed in gaseous medium. This is what we refer to solid aerosols. Good example is smoke, dust. We have a drug called epinephrine by titrate inhalation aerosol. It also fall under this category. So where we have our dispersed phase as a liquid dispersed in a gas, this is what we refer to as liquid aerosols. And examples, we have clouds, mist, fog, nasal sprays. We also have formulation povidone iodine, topical aerosol solution will form under this category. So what happens when you have a gas dispersed in a gas? What is the colloid type formed? Anyone from the class? What happens when you have a gas dispersed in a gas? Can I call out names? There are people who've joined with the listen only option. I don't know, these people don't want to speak. And why have most of you joined with the listen only option? This is very dangerous, eh? I may not be sure that you're there. Those who've joined with the listen only option, can you switch to the microphone? Anyway, we have Amina Bashir. Amina Bashir, what happens when you have a gas dispersed in a gas? Remember, we are looking at the physical state of nature. So we've looked at all the other states apart from having a gas dispersed in a gas. Amina Bashir?
Yes.
Yes, what happens when you have a gas dispersed in a gas? What is the colloid type formed?
I have no idea.
Okay, I'm trying to think because, well, how can gas be dispersed in gas? Or maybe you just form air.
Okay. Okay, any other last attempt we can listen from the class?
Hello.
Yes, Daniel Waruing. Is it Daniel Waruing? There's somebody who has logged in with his registration number. Yes, Daniel. When you have a gas dispersed in a gas.
I think it be hard, maybe physically.
It's impossible.
So I think it doesn't exist. Yeah.
No. You can't have two mixtures of gases. That's what you're trying to say. And remember, air is a mixture of gases, eh? The air that we breathe. Somebody had an idea, but it's only that he was expressing it in an unclear way. Let's listen to a lady. We have Rose Boyani. It exists, but does it form a colloid type? That's the question.
Hello?
Yes.
I think it will be a gaseous mixture.
Will it form a colloid solution, a colloid dispersion?
I don't know.
Wow. What's the particle size range of gases? Anyway, what happens when gases are mixed? They form true solutions. They don't form colloidal solutions. That's what happens. So it will not form a colloid. A mix of a gas and a gas will form a true solution. A molecular dispersion that is. So we can look at the other aspect of classification. So we have classification by physical state. So we can also have classification by interaction with the dispersion medium, how the dispersed phase interacts with the dispersion medium. And in this case, we have three classes. We have lyophilic colloids, we have lyophobic colloids, and we have association colloids. So lyophilic colloids. So this is a colloidal system in which the dispersed particles or the dispersed phase has a high affinity for the dispersion medium. So the dispersed phase highly interacts with the dispersion medium. These are also referred to as solvent-loving colloids. So due to the appreciable interaction with the dispersion medium, lyophilic colloids are easy to form. They are easy to form, or rather they form spontaneously. They also undergo what we call solvation, which involves the attachment of solvent molecules to the colloid particles. So where water is the dispersion medium, we call this phenomenon hydration. And they tend to be thermodynamically stable. So how do we classify lyophilic colloids? They're divided into two. We have hydrophilic colloids, now where the dispersion medium is water. So where a colloid appreciably interacts with water, that one we term it as a hydrophilic colloid. And we also have lipophilic colloids. Lipophilic colloids is where the dispersion medium is an organic solvent. Hydrophilic colloids may further be subdivided into true solutions. And a good example are water-soluble polymers, such as acacia, povidone. We also have gelled solution. And in this case, the polymers are dissolved in very high concentration. The example is methyl cellulose and gelatin. And we have particulate dispersion, whereby we have discrete solid particles dispersed in a medium. And a good example is microcrystalline cellulite and bentonite. Now, examples of lyophilic colloids, you find that most lyophilic colloids are formed of organic molecules dispersed in water or organic molecules dispersed in organic solvents. So for hydrophilic colloids, whereby water is the dispersion medium, and we have a range of gelatin, acacia, starch, insulin, albumin. On the other hand, for lipophilic colloids, whereby they are dispersed in organic solvents, you have rubber and polystyrene dispersed in organic solvents. You also have activated charcoal dispersed in oils to form lyophilic colloids, lipophilic colloids rather. So the other category is lyophobic colloids. So from the word phobic, find that the dispersed phase has very little attraction, if any, for the dispersion medium. And these we refer them to as solvent-hating colloids. So due to the little or no attraction of the dispersion medium between the dispersed phase and this, they are called solvent hating colloids. And due to this very little attraction, find that as compared to the lyophilic colloids, these ones are very difficult to form. They don't form spontaneously. And they are also thermodynamically unstable. And they lack solvation observed in hydrophilic colloids. They are also divided into two based on the interaction, and the little interaction with the dispersion medium. We have hydrophobic, which are water hating, and lipophobic, which are lipid hating or organic solvent hating colloids. So examples, so you'll find that lipophobic colloids will generally be composed of inorganic particles dispersed in water that will now form hydrophobic colloids. And examples, we have oils, waxes, magnesium stearate, gold, silver, arsenic sulfide, and silver iodide. Somebody has raised a hand. Yes, Beth Mudoni. Beth Mudoni? Is Beth Mudoni there? I can see your hand is raised. Okay, we can continue. So the other third category, based on the association between the dispersed phase and the dispersion medium, we have what we call association or amphiphilic colloids. So association, or rather amphiphilic colloids, are formed by the grouping of self-association of solids called amphiphiles or surface active agents. So amphiphiles are molecules that exhibit both lyophilic and lyophobic characteristics. So they exhibit both solvent-loving and solvent-hating characteristics. And we are told at low concentration, amphiphiles will exist separately and they will not form colloids. However, at high concentration, they aggregate to form several monomers greater than or equal to 50, leading to what we call a micelle formation. So at high concentration, they form micelles. And the concentration at which micelles are formed is what we call the critical micelles concentration. I think you come across the word micelles. So just like lyophilic colloids, association colloids also form spontaneously, provided that the concentration of the amphiphiles in solutions exceeds the critical micelle concentration. So remember, these exhibit both solvent-hating and solvent-loving properties or other characteristics. So this is just an illustration of the concentration at which micelles form. You'll find that when the solution is extremely dilute, the amphiphiles, I forgot to tell you, they'll have a hydrophilic head and hydrophobic tail. Association colloids. The amphiphiles will be formed of a hydrophilic head group, which has solvent-loving characteristics, and a hydrophobic tail, which has solvent-hating characteristics. So when the solution is extremely dilute, they'll exist separately. So as you keep on increasing the concentration of the solution, they start to aggregate. And when the solution is at the critical micelle concentration, CMC, they form a micelle. So you can see this is a micelle that now will have a hydrophobic core because of the hydrophobic tails and has hydrophobic head groups. So when the solution is above the critical micelle concentration, you have several micelles forming in your solution. So this is just to further illustrate the composition of your amphiphils. You have a hydrophobic head and a hydrophilic tail that aggregates together to form a micelle when the concentration is above the critical micelle concentration. So association colloids are composed of micelles. So we also have classifications and examples of association colloids. We have the anionic, and a good example is sodium lauryl sulfate. This is a surfactant that is commonly used in pharmaceutical formulations. We have cationic, and a good example is cetyl trimethyl ammonium bromide. Non-ionic association colloids. Good example is polyoxyethylene lauryl ether. These are all surfactants. Last but not least, we have zeta-ionic, where we have dimethyl dodecyl ammonium propane sulfonate. So we have 4 categories: anionic, cationic, anionic, and zeta-ionic surfactant, forming the classifications of association colloids. So how do we prepare our colloidal solutions? Now, it's important to note that lyophilic and association colloids are easy to form, or rather form spontaneously. So these ones, you can form them by simply mixing of the dispersed phase ingredients with a dispersion medium. And a good example is when you dissolve acacia or gelatin in water, or a celluloid in now this is an organic solvent. As you dissolve a celluloid in amyl acid to form a sol. Now, on the other hand, lyophobic, and therefore we employ several methods. You have dispersion methods, and dispersion methods will involve the reduction of size of coarse particles by input of energy. So you reduce coarse particles to form colloidal particles, but you require energy. So you can use ultrasonic methods, electrical methods, or simply shearing. You can also use milling and grinding processes. However, their efficiency is low. And it's important to note that colloidal mills or colloid mills reduce only a small amount of the total particles to the colloidal size range. So they are not that efficient in forming lyophobic colloids. So we also have condensation methods you can use to form lyophobic colloids. Now, condensation methods will involve the aggregation of subcolloidal size dispersed phase particles into colloidal particles, so which involves a high degree of initial supersaturation followed by formation and growth of nuclei. So you start with the subcolloidal particles to form colloidal particles. So supersaturation may be obtained by change in solvent or reduction in temperature. And a good example is when you have sulfur dissolved in alcohol to form a concentrated solution that is then poured in excess of water. You'll experience the growth of small nuclei in the supersaturated solution to form a colloidal solution. Now, we also have other condensation methods that involve chemical reactions, such as oxidation, reduction, and double decomposition. So for oxidation, we have the oxidation of hydrogen sulfides to form sulfur atoms and the production of sulfur sol, which is colloidal solution. And this happens when you pass hydrogen sulfide gas through sulfur oxide. So you can have oxidation by passing hydrogen sulfide gas through sulfur oxide. You can also have hydrolysis of ferric chloride to form ferric oxide sol. And this happens when you simply add ferric chloride solution to a large amount of water to undergo hydrolysis to form a red sol of ferric oxide. You can also have chromium and aluminium salts being hydrolyzed in water to form their respective sols. Now, last but not least, you also have double decompositions between hydrogen sulfide and arsenious acid, resulting in the formation of arsenious sulfide sol. So that's how you can prepare your lyophobic colloidal versions. So as you come to the end, there's a simple summary. I think when I send you the notes, you'll be able to read this. This is just a comparison of the properties of colloidal sols, acyclic associations, and lyophobic colloids. So I intended it to be a short lecture just to introduce the unit. So I propose that we may stop here for today, unless there is a question. So I'll be sending you these notes. So you don't need to worry about the notes. I'll be sending them to your class email. So that brings us to the end of our lecture for today. We'll just introduce the unit.